What's going on, linear algebros? It's Mr. C here, and in this video I'd like to show you how to solve the last example of the section 3.4 note packet. Well, actually I'll just be doing parts A and B in this video and part C in a separate one. With this last example, what we want to do is compare the general solution to two systems that we're going to identify as corresponding. If you look at the matrices here, or the systems given here, both in matrix equation format, you could probably tell quite easily why they would be considered corresponding linear systems. If you look at the coefficient matrix in each of these, they're exactly the same. Of course, the major difference between these two linear systems is that one would be homogeneous and the other would be non-homogeneous. In particular, the system that's on the left, this guy, is a homogeneous linear system, which I'll just write as capital H, and then this one would be non-homogeneous. For part A, we want to find a general solution of the homogeneous linear system. So that's the system on the left. What we'll want to do is go ahead and throw it into an augmented matrix format setting. Top row will have entries 1, -2, 3, 0. Second row, 2, 1, 4, 0. Third row, 1, -7, 5, and 0. Now what I would do is just quickly put that in the calculator and have it RREF it for you. And what you'll get is the following: 1, 0, 11 fifths, 0 as the top row entries. Middle row entries are going to be 0, 1, -2 fifths, 0. And the third row is going to consist of all zeros. Now, based on the entries in this reduced row echelon format of the augmented matrix, we're going to need a parameter. And the variable that is going to be assigned the parameter, the only variable that is the variable z. So based on this, we should say let z equal t. What this would imply about the variable x is that x is equal to -11 fifths t. I'm getting that from imagining the top row written out as an equation again. It would be x plus 11 fifths z equals 0. And subbing in the parameter and solving for x, you would get this parametric equation, x equals -11 fifths t. In a similar vein, y would equal +2 fifths t, and then z would equal t. Last thing to do is to write the set of parametric equations in an ordered triple format. So the first component of the ordered triple, or solution vector I should say, is the parametric equation for x, which is -11 fifths t. Second component, 2 fifths t. And then third component, t. And what you're looking at right here is the general solution to the homogeneous linear system, which why don't I just go ahead and write that as GSH, general solution for the homogeneous linear system. All right, so that takes care of part A. Let's now move on to part B, where it says, noting that 1, 1, 1 is a solution to the non-homogeneous linear system, find a general solution to the non-homogeneous linear system. So the wording seems like it's going to be a really difficult task, but actually it's pretty quick and easy, and what allows it to be such is the following result. What you can do is just take this specific ordered triple, which is a specific solution to the non-homogeneous linear system, and attach it to the general solution of the homogeneous linear system. So check this out. I'm going to write it out this way. General solution to the non-homogeneous linear system has the following format. The solution vectors x is going to equal a specific solution i.e. 1, 1, 1, plus the general solution of the homogeneous linear system. So I'll simply put GSH. Basically, all we have to do is say that the solution vectors x is equal to 1, 1, 1 plus what we got from the answer to part A. Negative 11/5 t, first component of that vector, 2 over 5t, and then t. And that right there would be the general solution to the non-homogeneous linear system. In the next video, we'll go ahead and verify that this is the correct answer by solving the non-homogeneous linear system directly. That's it for now. So thanks for watching, and please let me know if you have any questions whatsoever. Have a good one.